This lecture is for Chemistry in the Earth System, finishing up Unit 1.1, Heat. Our last essential question for this section: how can applying the law of conservation of energy help solve calorimetry problems? How can applying the law of conservation of energy help solve calorimetry problems? Calorimetry. Calorimetry. The total energy in an isolated system is conserved. Again, in an isolated system, total energy is conserved. This makes it possible to solve problems in which an amount of thermal energy is transferred from one substance to another with known thermal properties. Calorimetry is the study of the thermal energy changes that occur in a nearly isolated system. The heat energy transferred by an object or substance going through a temperature change is expressed by the equation that you see on your screen here. Q is equal to M multiplied by C sub S, or C by itself, multiplied by a delta T, where Q is the amount of heat, M is the mass of the substance, C, or C sub S, is the specific heat, and delta T is the temperature change. This equation, combined with the understanding that energy is conserved, again, in an isolated system, in a closed system, we can use this equation to solve calorimetry problems. So let's take a look at a calorimetry sample problem. So consider a 2.50 kilogram sample of hot copper. That hot copper is at 98.0 degrees Celsius. And this sample is dropped into a tank containing 10.0 kilograms of water, which is at 15 degrees Celsius. As thermal energy transfers from the copper to the water, again seeking thermal equilibrium, the metal's temperature decreases while the water's temperature increases. Because energy is conserved, the thermal energy removed by heat from the copper will equal the heat transfer to the water. Both copper and water will arrive at the same final temperature, which is the temperature of thermal equilibrium, or T sub EQ. Again, stands for thermal equilibrium. So the calculation is find the thermal equilibrium. Solve for T sub EQ. So let's take a look at the solution. So using the previous equation, and we can recall that the specific heat of water is 4,186 joules per kilogram degree Celsius. So the amount of heat received by the water is equal to the Q of the water, again, which is 10 kilograms, that's M, multiplied by 4,186 joules per kilogram degree Celsius, which again is the specific heat of the water, multiplied by TEQ, negative 15 degrees Celsius. So when we solve for this, we have 41,860 joules per degree Celsius, TEQ minus 627,900 joules. Now, at the same time, copper has a specific heat of only 386 joules per kilogram times degree Celsius. And it has cooled from 98.0 degrees Celsius to the thermal equilibrium, which again, we don't know, we're solving for. We know that the Q of the copper is going to be equal to 2.5 kilograms multiplied by the specific heat, which is 386 joules per kilogram degree Celsius, again multiplied by 98 degrees Celsius minus the thermal equilibrium, T sub EQ, which we can solve to represent as 94,570 joules minus, subtract 965 joules per degree Celsius, again, multiplied by thermal equilibrium, T sub EQ. Now, here's where we get to apply the law of conservation of energy. Because of the law of conservation of energy, the fact that energy is conserved in a closed or isolated system, we know that the Q, or heat transfer, of the water is going to be equal to Q of the copper. Thus, or therefore, meaning with this in mind, we can set the two terms, Q water, equal to Q copper. And so we'd take what we already figured out, the 41,860 joules per degree Celsius multiplied by T sub EQ minus 627,900 joules, and set that equal to 94,570 joules, subtract 965 joules per degree Celsius multiplied by T sub EQ. Then we can simply use our algebra skills, right? Solving algebraically for T sub EQ, and then rounding for appropriate number of significant figures, which in this case would be 3, we would find that the thermal equilibrium is 16.9 degrees Celsius. At this point, you should be able to fully and appropriately respond to today's essential question: how can applying the law of conservation of energy help solve calorimetry problems?